All right, we're back. We are on page 5 of notes 14 of Calc C. We're talking about the logistic differential equation. This has a nice summary, I think, of some of the information. So we're given the differential equation. Got to memorize that. The key part is really 1. If you don't have 1, nothing is what it seems. But as soon as you factor it, make it into a 1, now you have a lot of stuff memorized. So what are the things you have memorized? What's the population when the population is growing the fastest? Well, it's going to be y equals L over 2. That's your point of inflection. Where does the function have a point of inflection? Well, it's always when y equals L over 2. And then the x coordinate is actually always the natural log of a over k. But like, don't bother memorizing that. Solve it. Don't memorize, right? There's enough things in life to memorize. That is not a hard equation to solve, so just solve it. What is the limit as x approaches infinity? The limit as x approaches infinity of y is always L. L is called the carrying capacity of the population. Why? Because it's the limit. Because L is the limit. So all populations tend toward that amount. So that's the amount that you can have. Like ultimately, that's what you're going to end up with. That's your carrying capacity. If y is less than L, then what is true about dy dx? Dy dx will be greater than 0 if y is less than L. If y is greater than L, dy dx, what is true of dy dx? So dy dx is greater than 0, population increases. And then this is the opposite. If dy dx is, if y is greater than L, then people are going to die. Well, not people, probably deer or bacteria. I find most things are bacteria because it's like, you know, nobody cares about those basically, I guess. I don't know. I'm sure someone does. Your population decreases to L, I should say to L. But never gets there. You never get there. The only way that you get to L is if you start at L. And then is it even logistic? Not really. All right, let's see. I think we could probably do this. I think we can do this. So this problem is weird, sort of, because it's not the way it should be, right? Like this should be a 1. So I'm gonna rewrite this and say that this is, divide everything I see by 5. So I get 300, 1 plus, I would get 60, so I guess I get 59. I would get 60 if it was 300 divided by 5, but it's 5 less than that, so 1 less than 60. Negative 0.9 t. All right, how many people had it? That's plug in 0, you get, so that'd be p of 0, which is 300 over 60, so 5. 5 people had it. How many people will get it? It looks like 300, because that is the limit. When was the disease spreading most rapidly? Okay, so this is at p equals 150, which is half of the limit, right? So I need to solve that. So 150 equals 300 over 1 plus 59 e to the negative 0.9 t. We could solve, so it's like, you get 1 plus 59, you get this thing, the denominator, is equal to 2, then subtract 1, so you get this thing is equal to 1, then divide by 59, so you get this thing is equal to 1 over 59. Take the natural log, so you get this thing equals the natural log of 1 over 59, divide by negative 0.9, and you end up with t equals the natural log of 59 over 0.9. That is when the disease is spreading the most rapidly. I'm gonna do that. How fast was the disease spreading at the peak of the epidemic? So the peak of the epidemic is when the disease is spreading the most rapidly. So that's when p is equal to 150. So what do I want to do for that? I think I'm going to write the, so the differential equation would be dp dt, I guess. So dp dt is going to be k, which is 0.9. P, and then 1 minus P over 300. Right, so I've written the differential equation just by peeling off the values that I knew. Like I knew L was 300, I know that K is 0.9, and that's all you need to write the differential equation. So I wrote that, and now I need to plug in 150. So dp dt slash p equals 150 is going to be 0.9 times 150 and then times 1/2. Okay, so I don't know, 135 divided by 2. So where'd I get 135? I did 1/10 of 150 would be 15, but I need 9/10, so I just subtracted 15 to get just 135, and then you divide by 2. I believe that that is the rate. When did the spread of the disease start to slow down? So you get asked the same question. It's at the point of inflection. The answer to like almost every one of these questions is the point of inflection. So this is the same answer. T is natural 59. It's when you reached 150, right? As soon as half of the things have it, it's going to slow down. The growth is going to slow down. What is the differential equation? Done. I don't know how you would answer the previous part without that. I guess I'll write it again. dp dt is 0.9 p 1 I hope the next one asks us basically about the point of inflection again. By the time 200 people, okay, well, when 200 people had, so this will be, this makes me feel like I answered one of the other questions wrong. Slash p is 200, so this will be 0.9, 200, 1 minus 200 over 300, so 2/3, so 1/3. So 0.3 times 200. And then 1/10 would be 20, so 3/10 is 60. So I think 60 is 60 somethings per something, like people per unit of time, people per week, if you go back and read. People per week. And there you go. Good question. A lot of questions about the point of inflection. Point of inflection appears to be by far the most interesting part, according to questions. I think the limit tends to be the most interesting. But all right, we're done with this page. I'm gonna wrap up the video. I will see you in the next one when we'll be doing more stuff.